Unit 2, Describing Fundamental Principle of Machine Learning on Azure. By the end of this unit, you should be able to Identify common machine learning techniques. Describe core machine learning concepts, and explain Azure machine learning capabilities. Lesson 1, Identifying Common Machine Learning Techniques. Introduction. In this unit, we will explore the fundamentals of machine learning, ML, including key tasks like classification, regression, and clustering. We'll also dive into how Microsoft Azure enables efficient ML model development, training, and deployment through its powerful cloud-based tools and services. Topic 1, Understanding Key Concepts of Machine Learning. In this topic, we will explore the key concepts of machine learning, focusing on how machines learn from data to make decisions and predictions. We'll be introduced to core techniques like supervised and unsupervised learning, as well as important tasks such as regression, classification, and clustering. Machine learning. It is a subset of AI that enables computers to learn and improve from experience without explicit programming. It allows systems to analyze data, identify patterns, and make predictions or decisions without constant human intervention. The fundamental idea of machine learning is to use data from past observations to predict unknown outcomes or values. The proprietor of an ice cream store might use an app that combines historical sales and weather records to predict how many ice creams they're likely to sell on a given day, based on the weather forecast. Types of machine learning. Supervised learning. It is a general term for machine learning algorithms in which the training data includes both feature values and known label values. Supervised machine learning is used to train models by determining a relationship between the features and labels in past observations, so that unknown labels can be predicted for features in future cases. Unsupervised learning. It involves training models using data that consists only of feature values without any known labels. Unsupervised machine learning algorithms determine relationships between the features of the observations in the training data. Under these two main types of ML, there are different forms of machine learning that we can use in making decisions or predictions. A breakdown of common types of machine learning is shown in the following diagram. Regression machine learning. It is a type of supervised learning where the goal is to predict a continuous numerical value based on input data. In regression tasks, the output variable is a real-valued number, and the model learns the relationship between the input features and the target variable. Classification machine learning. It is also a type of supervised learning, but in this case, the goal is to predict a discrete class or category, not a continuous value. The output variable is a category label, example spam or not spam, dog or cat. Clustering machine learning. It is a type of unsupervised learning where the goal is to group similar data points into clusters. Unlike regression and classification, clustering doesn't have labeled data, and the model must identify the inherent structure or patterns in the data without predefined classes or labels. We will learn more about the different types of machine learning tasks in the next topics. Topic 2, Identifying regression machine learning scenarios. Topic 3, Identifying classification machine learning scenarios. In this topic, we'll dive into classification in machine learning, a technique used to categorize data into distinct classes based on input features. We'll also explore the essential steps in training a classification model. Regression machine learning scenario. Classification. It is a type of supervised learning in machine learning where the goal is to predict a discrete label or category for each input based on historical data. Classification machine learning. Unlike regression, where the model predicts continuous values, classification models aim to categorize data into predefined classes. Each input data point is assigned to a specific class based on its features. Binary and multi-class classification are two types of classification tasks in machine learning. Binary classification machine learning. Binary classification algorithms are used to train a model that predicts one of two possible labels for a single class. Essentially, predicting true or false. In most real scenarios, The data observations used to train and validate the model consist of multiple feature, x, values and a, y, value that is either 1 or 0. Multicast classification learning. It is used to predict to which of multiple possible classes an observation belongs. It follows the same iterative train, validate, and evaluate process as regression and binary classification, in which a subset of the training data is held back to validate the trained model. Let's explore the steps in training binary and multi-class classification ML models. Topic 3. Identifying classification machine learning scenarios. Identifying binary classification machine learning scenarios. Let's explore the process of training a binary classification machine learning model, where the goal is to predict one of two possible classes. Binary classification machine learning scenario. Binary classification. Machine learning. Binary classification is a supervised learning algorithm that categorizes data into one of two classes or categories. The classes are usually labeled as positive and negative, yes and no, or 1 and 0. To understand how binary classification works, let's look at a simplified example that uses a single feature, x, to predict whether the label, y, is 1 or 0. Sample scenario. We'll use the blood glucose level of a patient to predict whether or not the patient has diabetes. Let's take a look at our data on the next slide. Using the dataset, let's train our binary classification ML model. Step 1 of training a binary classification ML model. Step 1. Split the data. To start, let's split the data for the training. Like what we did in the regression ML model training, we will use some of the data for the training, and some for the validation. To train the model, we will use a classification algorithm. Step 2 of training a binary classification ML model. Step 2. Use an algorithm. To train the model, we'll use an algorithm to fit the training data to a function that calculates the probability of the class label being true, in other words, that the patient has diabetes. Probability is measured as a value between 0.0 and 1.0, such that the total probability for all possible classes is 1.0. So for example, if the probability of a patient having diabetes is 0.7, then there's a corresponding probability of 0.3 that the patient isn't diabetic. There are many algorithms that can be used for binary classification, such as logistic regression, which derives a sigmoid, S-shaped, function with values between 0.0 and 1.0. Note, despite its name, machine learning logistic regression is used for classification, not regression. The important point is the logistic nature of the function it produces, which describes an S-shaped curve between a lower and upper value, 0.0 and 1.0 when used for binary classification. The function produced by the algorithm describes the probability of y being true, y equals 1, for a given value of x. Mathematically, you can express the function like this. F, x, equals p, y equals 1x. For 3 of the 6 observations in the training data, we know that y is definitely true, so the probability for those observations that y equals 1 is 1.0, and for the other 3, we know that y is definitely false, so the probability that y equals 1 is 0.0. The S-shaped curve describes the probability distribution so that plotting a value of x on the line identifies the corresponding probability that y is 1. The diagram also includes a horizontal line to indicate the threshold at which a model based on this function will predict true, 1, or false, 0. The threshold lies at the midpoint for y, p, y, equals 0.5. For any values at this point or above, the model will predict true, 1, while for any values below this point it will predict false, 0. For example, for a patient with a blood glucose level of 90, the function would result in a probability value of 0.9. Since 0.9 is higher than the threshold of 0.5, the model would predict true, 1, in other words, the patient is predicted to have diabetes. Step 3 of training a binary classification ML model. Step 3. Validate the model. As with regression, when training a binary classification model, you hold back a random subset of data with which to validate the trained model. Let's assume we held back the following data to validate our diabetes classifier. Applying the logistic function we derived previously to the x values, we get this plot. Based on whether the probability calculated by the function is above or below the threshold, the model generates a predicted label of 1 or 0 for each observation. We can then compare the predicted class labels, y, to the actual class labels, y. Let's move on to the last step in our training process. Step 4 of training a binary classification ML model. Step 4. Calculate the evaluation metrics. The first step in calculating evaluation metrics for a binary classification model is usually to create a matrix of the number of correct and incorrect predictions for each possible class label. This visualization is called a confusion matrix, and it shows the prediction totals where y equals 0 and y equals 0, true negatives, Tn. y equals 1 and y equals 0, false positives, Fp. y equals 0 and y equals 1, false negatives, Fn. y equals 1 and y equals 1, true positives, Tp. The arrangement of the confusion matrix is such that correct, true, predictions are shown in a diagonal line from top left to bottom right. Often, color intensity is used to indicate the number of predictions in each cell, so a quick glance at a model that predicts well should reveal a deeply shaded diagonal trend. Below are some of the metrics you can calculate from the confusion matrix. 1. Accuracy. The simplest metric you can calculate from the confusion matrix is accuracy, the proportion of predictions that the model got right. Accuracy is calculated as Tn plus Tp, divided by Tn plus Fn plus Fp plus Tp. 2. Recall. It is a metric that measures the proportion of positive cases that the model identified correctly. In other words, compared to the number of patients who have diabetes, how many did the model predict to have diabetes? The formula for recall is Tp divided by Tp plus Fn. 3. Precision. It is a similar metric to recall, but measures the proportion of predicted positive cases where the true label is actually positive. In other words, what proportion of the patients predicted by the model to have diabetes actually have diabetes? The formula for precision is Tp divided by Tp plus Fp. 4. F1 score. 2x precision x recall, divided by precision plus recall. It is an overall metric that combined recall and precision. The formula for F1 score is, for our diabetes example, 2x 1.0 x 0.75, divided by 1.0 plus 0.75. Equals 1.5 divided by 1.75. Equals 0.86. We will explore how to train another classification ML, multi-class classification machine learning model, in the next topic. Topic 3, Identifying classification machine learning scenarios. Identifying multi-class classification machine learning scenarios. Let's dive into training a multi-class classification machine learning model, where the goal is to predict one of several possible classes. Multi-class classification machine learning scenario. Multi-class classification. It is used to predict to which of multiple possible classes an observation belongs. As a supervised machine learning technique, it follows the same iterative train, validate, and evaluate process as regression and binary classification, in which a subset of the training data is held back to validate the trained model. Let's explore an example in which we have some observations of penguins, in which the flipper length, x, of each penguin is recorded. For each observation, the data includes the penguin species, y, which is encoded as follows. 0, Adelie. 1, Gentoo. 2, chin strap. Note, as with previous examples in this module, a real scenario would include multiple feature, x, values. We'll use a single feature to keep things simple. Using the dataset, let's train our multi-class classification ML model. Step 1 of training a multi-class classification ML model. Step 1. Split the data. To start, let's split the data for the training. Like what we did in the regression and binary classification ML model training, we will use some of the data for the training, and some for the validation. To train the model, we will use a classification algorithm. Step 2 of training a multi-class classification ML model. Step 2. Use an algorithm. To train a multi-class classification model, we need to use an algorithm to fit the training data to a function that calculates a probability value for each possible class. There are two kinds of algorithm you can use to do this. 1vs REST algorithms train a binary classification function for each class, each calculating the probability that the observation is an example of the target class. Each function calculates the probability of the observation being a specific class compared to any other class. For our penguin species classification model, the algorithm would essentially create three binary classification functions. OF0, x, equals p, y equals 0x. OF1, x, equals p, y equals 1x. OF2, x, equals p, y equals 2x. Each algorithm produces a sigmoid function that calculates a probability value between 0.0 and 1.0. A model trained using this kind of algorithm predicts the class for the function that produces the highest probability output. As an alternative approach is to use a multinomial algorithm, which creates a single function that returns a multi-valued output. The output is a vector, an array of values, that contains the probability distribution for all possible classes, with a probability score for each class which when totaled add up to 1.0, f, x, equals p, y equals 0x, p, y equals 1x, p, y equals 2x. An example of this kind of function is a softmax function, which could produce an output like the following example, 0.2, 0.3, 0.5. The elements in the vector represent the probabilities for classes 0, 1, and 2 respectively, so in this case, the class with the highest probability is 2. Regardless of which type of algorithm is used, the model uses the resulting function to determine the most probable class for a given set of features, x, and predicts the corresponding class label, y. Step 3 of training a multi-class classification ML model. Step 3. Validate multi-class classifier. You can evaluate a multi-class classifier by calculating binary classification metrics for each individual class. Alternatively, you can calculate aggregate metrics that take all classes into account. Let's assume that we have validated our multi-class classifier. Let's say we have obtained the following results during the validation. The confusion matrix for a multi-class classifier is similar to that of a binary classifier, except that it shows the number of predictions for each combination of predicted, y, and actual class labels, y. The confusion matrix for a multi-class classifier is similar to that of a binary classifier, except that it shows the number of predictions for each combination of predicted, y, and actual class labels, y. From this confusion matrix, we can determine the metrics for each individual class. Step 4 of training a multi-class classification ML model. Step 4. Calculate the evaluation metrics. To calculate the overall accuracy, recall, and precision metrics, you use the total of the TP, TN, FP, and FN metrics. Overall accuracy equals 13 plus 6, divided by 13 plus 6 plus 1 plus 1, equals 0.90. Overall recall equals 6 divided by 6 plus 1, equals 0.86. Overall precision equals 6 divided by 6 plus 1, equals 0.86. The overall F1 score is calculated using the overall recall and precision metrics. Overall F1 score equals 2x 0.86 x 0.86, divided by 0.86 plus 0.86 equals 0.86. Let's now take a look at how training an unsupervised ML model looks like in the next topic. Topic 4, Identifying Clustering Machine Learning Scenarios. In this topic, we'll dive into clustering, a key technique in machine learning for grouping similar data points without needing labels. Clustering Machine Learning Scenario. Clustering. A form of unsupervised machine learning in which observations are grouped into clusters based on similarities in their data values, or features. Clustering machine learning. This kind of machine learning is considered unsupervised because it doesn't make use of previously known label values to train a model. In a clustering model, the label is the cluster to which the observation is assigned, based only on its features. Sample scenario. For example, suppose a botanist observes a sample of flowers and records the number of leaves and petals on each flower. The goal is not to identify the different types, species, of flower, just to group similar flowers together based on the number of leaves and petals. There are no known labels in the dataset, just two features. This is just an example of how a dataset looks like in clustering ML. Training a clustering ML model. Step 1. Prepare the data. Clustering algorithms work with unlabeled data, meaning there is no target variable or predefined class labels for the data points. The algorithm must find patterns and groupings without explicit supervision. Just like in the example given previously, there are no labels in the dataset, just features. Step 2. Use an algorithm. There are multiple algorithms you can use for clustering. One of the most commonly used algorithms is k-means clustering. Step 1. Vectorize the feature, x, values. The feature, x, values are vectorized to define n-dimensional coordinates, where n is the number of features. In the flower example, we have two features, number of leaves, x1, and number of petals, x2. So, the feature vector has two coordinates that we can use to conceptually plot the data points in two-dimensional space, x1, x2. Step 2, choose the number of clusters, k, and initialize centroids. You decide how many clusters you want to use to group the flowers, call this value k. For example, to create 3 clusters, you would use a k value of 3. Then k points are plotted at random coordinates. These points become the center points for each cluster, so they're called centroids. Step 3, assign data points to clusters. Each data point, in this case a flower, is assigned to its nearest centroid. Step 4, update centroids. Each centroid is moved to the center of the data points assigned to it based on the mean distance between the points. Step 5, reassign centroids based on the new closest centroid. After the centroid is moved, the data points may now be closer to a different centroid, so the data points are reassigned to clusters based on the new closest centroid. Step 5, reassign centroids based on the new closest centroid. The centroid movement and cluster reallocation steps are repeated until the clusters become stable or a predetermined maximum number of iterations is reached. Topic 4, Identifying Clustering Machine Learning Scenarios. Topic 5, Identifying Features of Deep Learning Techniques. For the last topic in this lesson, we'll discuss about deep learning, a powerful subset of machine learning that uses neural networks with many layers to solve complex problems. Deep learning. It is an advanced form of machine learning that uses artificial neural networks to simulate biological neurons through mathematical functions. Biological neural network. Network neurons fire in response to electrochemical stimuli. When fired, the signal is passed to connected neurons. Artificial neural network. Artificial neural networks are made up of multiple layers of neurons, essentially defining a deeply nested function. This architecture is the reason the technique is referred to as deep learning, and the models produced by it are often referred to as deep neural networks, DNNs. Deep neural networks, DNNs. They are used for regression, classification, natural language processing, and computer vision. It involves training a function f, x, that helps predict a label, y, based on the value of one or more features, x. How does a neural network learn? 1. The training and validation datasets are defined, and the training features are fed into the input layer. 2. The neurons in each layer of the network apply their weights, which are initially assigned randomly, and feed the data through the network. 3. Input data is passed through the network, layer by layer, to generate an output. The output layer produces a vector containing the calculated values for y. For example, an output for a penguin class prediction might be 0.3, 0.1, 0.6. 4. Input data is passed through the network, layer by layer, to generate an output. The output layer produces a vector containing the calculated values for y. For example, an output for a penguin class prediction might be 0.3, 0.1, 0.6. 5. Since the entire network is essentially one large nested function, an optimization function can use differential calculus to evaluate the influence of each weight in the network on the loss, and determine how they could be adjusted, up or down, to reduce the amount of overall loss. The specific optimization technique can vary, but usually involves a gradient descent approach in which each weight is increased or decreased to minimize the loss. 6. The changes to the weights are backpropagated to the layers in the network, replacing the previously used values. 7. The process is repeated over multiple iterations, known as epochs, until the loss is minimized and the model predicts acceptably accurately. Note, while it's easier to think of each case in the training data being passed through the network one at a time, in reality the data is batched into matrices and processed using linear algebraic calculations. Neural network training is best performed on computers with graphical processing units, GPUs, that are optimized for vector and matrix manipulation. We have covered the fundamental concepts of machine learning, including key techniques like regression, classification, and clustering, along with the powerful potential of deep learning. We will learn about more concepts about machine learning such as features, labels, and datasets in Lesson 2. Lesson 2, Describing Core Machine Learning Concepts. Introduction. This lesson helps learners identify features and labels in a dataset, essential for training and evaluating machine learning models. It forms the foundation for understanding how machine learning works. Topic 1. Identifying features and labels in a dataset for machine learning. In this topic, we will explore the key concepts of features and labels in machine learning. Understanding how to properly define and use features and labels is crucial for building effective machine learning models. Role of datasets in ML. Data is essential in machine learning, allowing algorithms to learn patterns and relationships between inputs and outputs for accurate prediction or classification. Humans learn through experience by observing patterns, making mistakes, and adjusting based on feedback. Similarly, machines in machine learning process data to identify patterns and make predictions without direct experience. Consider datasets as the ingredients for creating a delicious dish. Just as the quality of ingredients directly impacts the flavor and success of the dish, the quality of the data is crucial to the performance and accuracy of a machine learning model. In machine learning, a dataset is a collection of data used to train and evaluate models. It consists of numerous data points in a table, serving as raw material for AI to learn patterns, analyze trends, and make predictions. There are two important components of datasets: features and labels. Let's explore the differences between these two. Relationship between features and labels in a dataset. Features and labels. In a dataset. In machine learning, features and labels are fundamental components of the data used to train models. Understanding the distinction between them is crucial for building and applying machine learning algorithms effectively. Features are the input variables or attributes of a dataset that describe the characteristics of the data. They are the pieces of information that the machine learning algorithm uses to make predictions or classifications. Features can be of different types, including numerical, example age, income, or categorical, example color, gender. They represent the characteristics or properties that help in understanding or predicting a target outcome. Labels are the output values or target variables for prediction or classification, providing context to the data for training machine learning models. In supervised learning, the labels are the known outcomes, and the model's goal is to predict these labels based on the features. In regression tasks, the label is usually a continuous value. In classification tasks, the label is typically a category or class. To better understand the concepts, here is an example. In the ice cream sales scenario, our goal is to train a model that can predict the number of ice cream sales based on the weather. The weather measurements for the day, temperature, rainfall, wind speed, etc., would be the features, X, and the number of ice cream sold on each day would be the label, Y. Let's take a look at the dataset on the next slide. Understanding this distinction is crucial for building effective models, as the relationship between features and labels forms the foundation of supervised learning. We will learn more about datasets in the next topic. Topic 2, describing how training and validation datasets are used in machine learning. In this topic, we will explore the importance of training and validation datasets in the machine learning workflow. Splitting data is a crucial step in many data analysis and machine learning tasks and an essential step in many data analysis and machine learning processes. This involves dividing the dataset into three main subsets. Training. Splitting data is a crucial step in many data analysis and machine learning tasks and an essential step in many data analysis and machine learning processes. This involves dividing the dataset into three main subsets. Validation. Used for frequent model evaluation, helping data scientists fine-tune hyperparameters. While part of training, the model only sees this data for evaluation, ensuring an unbiased assessment and preventing overfitting for better generalization. Testing. The testing dataset is the gold standard for evaluating a fully trained model. Used only after training the model, it includes diverse scenarios to assess real-world performance. One that data scientists strive for is to make models that are robust, meaning they will give consistent results that are correct most of the time. This is where the training validation testing process comes in. Please take note that the test and validation sets are sometimes used interchangeably. In the next lesson, we will explore machine learning using Azure tools and services. Lesson 3, describing Azure machine learning capabilities. Introduction. This lesson explores Azure's automated machine learning, covering its features and functionalities. It also highlights various Azure data and compute services that support and enhance each stage of the machine learning lifecycle, particularly model deployment and management. Topic 1, describing capabilities of automated machine learning. In this topic, we'll dive into Microsoft Azure Machine Learning, a powerful platform that supports end-to-end machine learning workflows. We will also cover the capabilities of Azure ML Studio. Microsoft Azure Machine Learning, Azure ML, provides a robust ecosystem for managing the entire machine learning lifecycle, from data preparation to model deployment, making it easier for both beginners and experienced data scientists to work with machine learning. Azure ML designed to be used by data scientists, software engineers, DevOps professionals, and others to manage the end-to-end life cycle of machine learning projects, including define the task, exploring data and preparing it for modeling, monitoring and managing the model while reviewing and applying responsible AI principles and practices, training and evaluating machine learning models. Training and evaluating machine learning models. The primary resource required for Azure Machine Learning is an Azure Machine Learning Workspace, which you can provision in an Azure subscription. Other supporting resources, including storage accounts, container registries, virtual machines, and others are created automatically as needed. To create an Azure Machine Learning Workspace, you can use the Azure portal. Microsoft Azure Interface. https://azure.microsoft.com/n-us. After you've provisioned an Azure Machine Learning workspace, you can use it in Azure Machine Learning Studio, a browser-based portal for managing your machine learning resources and jobs. You may use this direct link to create your workspace and get to Microsoft Azure ML Studio. The screenshot on the next slide shows the metrics page for a trained model in Azure Machine Learning Studio, in which you can see the evaluation metrics for a trained multi-class classification model. We will tackle the different features and capabilities of Azure Machine Learning in the next topics. Topic 2, Describing Data and Compute Services for Data Science and Machine Learning. In this topic, we'll explore the relationship between data and compute services in Azure. By leveraging Azure's powerful data management and compute capabilities, organizations can efficiently store, process, and analyze vast amounts of data to derive valuable insights and drive decision-making. Data services in Azure. To train a machine learning model, you need access to the data you plan to use. So, before you start to experiment with machine learning models, make sure to identify the data sources and know which tools you want to use to load and transform the data. Microsoft Azure Data Services is a comprehensive suite of cloud-based services designed to manage, store, and analyze data. These services cater to a wide variety of needs, ranging from data storage to advanced analytics, and enable organizations to unlock the value of their data in a scalable and secure environment. Azure Data Storage Solutions. Azure Storage Accounts are the base storage type within Azure. Azure Storage offers a scalable object store for data objects and file system services in the cloud. Some common services related to data storage are Azure Blob Storage. Cheapest option for storing data as unstructured data. Ideal for storing files like images, text, and JSON. Often also used to store data as CSV files, as data scientists prefer working with CSV files. Azure Data Lake Storage. A more advanced version of the Azure Blob Storage. Also stores files like CSV files and images as unstructured data. A data lake also implements a hierarchical namespace, which means it's easier to give someone access to a specific file or folder. Storage capacity is virtually limitless, so ideal for storing large data. Azure SQL Database. Stores data as structured data. Data is read as a table and schema is defined when a table in the database is created. Ideal for data that doesn't change over time. Azure Data Ingestion Solutions. They provide a set of managed services and tools designed to simplify the process of moving data into Azure for analysis, processing, and storage. Azure Data Factory. A cloud-based data integration service that enables the movement and transformation of data across different sources. It's used for ETL, extract, transform, load, operations. Azure Event Hubs. A real-time data ingestion service used for collecting and processing streaming data from various sources like IoT devices and applications. Azure Data Preparation Solutions. They are a set of services and tools within Azure designed to help organizations clean, transform, and process data before it's used for analytics, machine learning, or reporting. Below are some key Azure Data Preparation Solutions. Azure Data Factory. In addition to ingestion, it provides powerful data transformation capabilities to prepare data for analytics. Azure Databricks. A collaborative Apache Spark-based platform for big data analytics and machine learning that enables advanced data preparation and transformation. Azure Data Management Solutions. They encompass a range of services designed to efficiently manage, store, govern, and protect data in the Azure cloud ecosystem. Below are the key Azure Data Management Solutions. Azure Purview. A unified data governance solution that provides data cataloging, classification, and data lineage tracking for managing data assets. Azure SQL Managed. A fully managed relational database that allows for better management and migration of on-premises SQL Server databases to Azure. Azure Data Catalog. A fully managed cloud service that helps organizations register, discover, and manage data assets. Azure Data Analytics Solutions. They provide businesses with the tools and technologies to derive insights from vast amounts of data, enabling organizations to make data-driven decisions. Below are the key Azure Data Analytics solutions. Azure Databricks. A cloud-based integrated analytics service that combines data warehousing and big data processing capabilities, enabling you to analyze both structured and unstructured data. Azure Synapse Analytics. A unified analytics platform for big data and machine learning, enabling collaborative data processing and advanced analytics on large data sets. Azure Stream Analytics. Real-time analytics service for streaming data, useful in scenarios such as IoT or live data monitoring. Once the data has been collected, compute services come into play to process, analyze, and model that data. Compute services in Azure. Compute services in Microsoft Azure. Compute services in Azure are designed to provide on-demand computing resources that enable users to run applications, workloads, and process data at scale. These services are essential for building, testing, deploying, and managing applications and services in the cloud. Some of the most common compute options in Azure are the following. Azure Virtual Machines. They are one of the core compute services offered by Microsoft Azure, enabling users to run virtualized computing environments in the cloud. With Azure VMS, you can create and use VMS in the cloud. VMS provide infrastructure as a service, IaaS, in the form of a virtualized server and can be used in many ways. These virtual machines allow you to run applications, operating systems, and workloads just like you would on physical hardware, but with the flexibility and scalability of the cloud. Azure Containers. While virtual machines are an excellent way to reduce costs versus the investments that are necessary for physical hardware, they're still limited to a single operating system per virtual machine. If you want to run multiple instances of an application on a single host machine, containers are an excellent choice. Containers are lightweight and designed to be created, scaled out, and stopped dynamically. It's possible to create and deploy virtual machines as application demand increases, but containers are a lighter weight, more agile method. They are designed to allow you to respond to changes on demand. With them, you can quickly restart if there's a crash or hardware interruption. Azure Functions. It is an event-driven, serverless compute option that doesn't require maintaining virtual machines or containers. If you build an app using VMS or containers, those resources have to be running in order for your app to function. With Azure Functions, an event wakes the function, alleviating the need to keep resources provisioned when there are no events. The goal of serverless computing is to help software developers focus on their other tasks by taking care of things such as installing an operating system or downloading system updates. This means that the responsibility of managing servers is already handled for you. There are 3 big benefits of using serverless approach. No infrastructure management. As a business, you don't have to focus on administrative tasks like installing an operating system. Instead, you simply deploy your code and it automatically runs with high availability. Scalability. As your application grows in popularity, your application will continue working under any workload. Serverless computers can scale from nothing to tens of thousands of requests without any configuration. Only pay for what you use. Using Azure to support serverless computing through products like Azure Functions, your main job will simply be to upload your code and you automatically get the benefits of infrastructure management and scalability plus a payment model that will only charge you for what you use. Compute services play a crucial role in ensuring that models are trained, validated, and deployed effectively. In the last lesson for this unit, we will learn about the last steps in machine learning. Topic 3, Describing Model Management and Deployment Capabilities in Azure Machine Learning. In today's fast-paced AI-driven world, deploying and managing machine learning models efficiently is crucial for delivering real-time, data-driven insights. In this topic, we'll explore how Azure's model management pipeline helps organizations manage and deploy models. Model management and deployment. The project life cycle can vary from project to project, but it often resembles this diagram. Define the task. Explore and prepare data. Train and validate model. MLOps, monitor and manage cycle. Deploy model. Once the model has been trained, it is ready to be deployed into a production environment. Deployment involves making the model accessible for real-time predictions or integrating it into an application or system. Below are the steps involved in the model management and deployment pipeline. Model development training. It involves designing and training machine learning models using available data. This step focuses on selecting the right algorithms, pre-processing techniques, and tuning hyperparameters to achieve optimal performance. Model packaging/serialization. Model packaging refers to the process of bundling the trained machine learning model with its dependencies into a format that can be easily deployed. Model serialization is the process of converting the trained model into a format that can be saved and shared for later use. Model registry. It is a centralized repository for storing and managing versions of machine learning models. It helps track different model versions, ensuring transparency and version control throughout the model lifecycle. Environment preparation. It involves setting up the necessary software, hardware, and dependencies required to run the model effectively in production. This can include configuring specific runtime environments, containers, or cloud infrastructure to support model execution. API development. It refers to the creation of an application programming interface that allows external systems to interact with the deployed model. It exposes model predictions as web services, enabling seamless integration with other applications. Model development. It is the process of taking a trained and packaged model and making it available in a production environment. It involves setting up the necessary infrastructure, such as servers or containers, to serve the model and handle incoming inference requests. Monitoring and logging. These involve tracking the model's performance and logging relevant data, example predictions, errors, usage. This helps ensure the model operates as expected and allows for prompt identification of any issues or anomalies in production. Updating and retraining. These involve tracking the model's performance and logging relevant data, example predictions, errors, usage. This helps ensure the model operates as expected and allows for prompt identification of any issues or anomalies in production. To better understand this process, let us use a sample scenario shown in the next part of the book. Model management and deployment pipeline. Let's go back to the key steps in model management and deployment pipeline. 1. Model development. The data science team develops the predictive maintenance model using Azure Machine Learning Studio to train it on historical sensor data collected from the equipment. The team uses Azure Databricks for advanced data pre-processing and feature engineering before training the model using machine learning libraries. 2. Model packaging and serialization. After training the model, the team uses the Azure Machine Learning SDK to package the model and its dependencies, example libraries, configuration files, into a Docker container. The trained model is serialized, saved, in the .pkl format and stored in Azure Blob Storage. This enables easy retrieval of the model when needed for deployment. 3. Model registry. The model is registered in the Azure ML Model Registry, allowing the team to track the model's version, metrics, and training pipeline. This step ensures that different versions of the model can be managed, evaluated, and deployed in a controlled manner. 4. Model environment. The deployment team prepares the environment by creating a custom Azure ML environment with all the required dependencies, example Python libraries like scikit-learn, pandas, numpy, for running the predictive maintenance model. Azure containers. They deploy the model in a containerized environment using Azure Kubernetes Service, AKS, for scalability and flexibility. 5. API development. The model is exposed as a REST API using Azure Functions to provide a serverless way to handle incoming inference requests. Azure API management is used to manage, monitor, and secure the API endpoints for external applications to consume the model's predictions. 6. Model deployment. The packaged model is deployed to Azure Kubernetes Service, AKS, which allows it to handle a large volume of real-time requests efficiently. AKS ensures the model can scale automatically based on traffic, providing high availability for mission-critical production environments. 7. Monitoring and logging. Once the model is live, the Azure Monitor and Application Insights services are used to continuously monitor the model's performance, track API usage, and detect any anomalies or failures. Logs and metrics are captured to track the model's response time, accuracy, and performance. Updating and retraining are crucial steps to ensure that the model remains accurate over time, especially as new data becomes available or the operating conditions of the manufacturing equipment change.